Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson I'm going to be describing 2D sediment options and tolerances. So what I have on the screen here is the first of 3 pages that I'm going to be going through for this lesson. If you see over here on the left menu, if you don't see the menu at all, you might have to expand your window out to the side a little bit. And then there's also these 2 other pages for the 2 different tabs, which we'll be covering. So I'm going to go ahead and minimize that. What you see on the screen is RAS Mapper. I have a 2D flow area that's sketched in across this river reach and then some of the floodplain area. And what we're going to be talking about in this lesson is if you go up to Run, Unsteady Flow Analysis, and then in the Options tab, you come down here to Sediment Computation Options and Tolerances. Now we have this dialog box, and this is what we're going to be focusing in on this particular lesson. What we have in this dialog box are 2 tabs. There's the General tab, and then this 2D Computational Options tab. So let's start with the General tab, and there will be a few 1D elements in this dialog box I'm going to sort of skip over because it's already been covered in previous lessons. All right, so what I want to start with here is this sediment computation multiplier. Now, sediment flow is oftentimes more computationally expensive than hydraulic flow and hydraulic calculations. So these sediment computations are not necessarily required for every hydraulic computation. Now, by default, the value is 1, which means there will be sediment calculations for every hydraulic time step, but that's not necessary. If you want it to be every 10, you can just set that value to 10, or every 5, that's fine. A typical range is between 5 and 20, according to the user's manual. So for instance, over here, if we have our computation interval set to 1 minute, and then over here we have it set to 5 as a multiplier, that means every 5 minutes is when the sediment computations will run. If over here we have a computation time interval of 10 minutes, and then over here it is 6, then that means once an hour or once every 60 minutes, the sediment computations will run. Okay? So that's just meant to help improve the computation time and hopefully not at the expense of accuracy or stability. Below that, we have sediment warm-up periods right here with 3 different values for concentration, gradation, and bathymetry. Now, with 1D warm-up periods, the way that worked is basically we had a specified duration of time that the simulation ran. We prepended that warm-up period in 1D before the actual duration of the simulation. But with 2D, it works a little bit different. First, you'll still have the same hydraulic warm-up period. That doesn't change. But the 2D sediment warm-up period will begin following the hydraulic warm-up period. And there's 3 stages for sediment. Well, there's only 2 stages for 1D, but for 2D sediment, there's also this first one, this concentration warm-up period. So you're going to go ahead and specify the number of days. HEC RAS will run the sediment model with constant flow, stage, and sediment boundary conditions associated with the first time step for both the concentration and for the gradation. And during this time, the sediment bed geometry will be forced to not change until some sort of equilibrium is reached, or I'm sorry, at least until the number of days has surpassed. With bathymetry, it's a little bit different. This is where the bed gradation is allowed to change. And what happens basically in this third and final sediment warm-up step for bathymetry is that divots get filled in, any mounds sort of get smoothed over, and the overall underwater terrain gets smoothed out a little bit. Below that, we have dynamic bed roughness predictors. So the bed roughness predictor options here is none. That's the default value. But we also have these options for Lee-Marinos, Brownlee, Von Ryn, and Kareem. Kareem's only for 2D flow. The user manual talks about these different methods, and also there's a page in the hydraulic reference manual that goes into details. For instance, Lee-Marinos is for coarse gravel and cobble channels. That's this one right here, where the grain roughness is the primary source of channel roughness. And then Brownlee is specifically used for larger rivers and so on. This page in the HEC RAS 2D sediment transport reference model manual, I'll go ahead and leave a link to this in the description as well. This has the different methods right here, and you can knock yourself out by reading through the theory and the equations about how they are used. But so if you don't know, then check out this reference to understand which method to use for your bed roughness predictor. All right, below that, we have to apply computed roughness to, and then either sediment only, that's the default value, or sediment and hydraulics. The reason why sediment only is selected as the default value is because hydraulic flow roughness may include other components in the roughness besides the bottom, such as vegetation. And then this last button here in the general tab deals with 1D flow, where you can actually specify different bed roughness data for different reaches or distances between cross sections by selecting the river, the reach, and then the range of cross sections, and then setting bed roughness reach data. All right, so let's move on. That was the general tab. Now we have the 2D computational options tab, and we start off in this transport frame with our advection scheme. Options are shown here: upwind, exponential, mid-mod, and harmonic. So advection scheme is referring to the numerical method used to represent how sediment moves with the flow of water. Upwind and exponential are simpler linear models. They run faster, and exponential, I read, is less diffusive than upwind. And then the other two methods here, mid-mod and harmonic, are nonlinear. They're more complex, and mid-mod is more diffusive than harmonic. All right, below that we have the sediment matrix solver, and then our options here are Paradiso and then FGMRES. These solver methods refer to the numerical method used to solve the system of equations governing sediment transport. So at this point, the user's manual sort of reads more like a technical reference manual, a little bit too detailed. But what you need to know is that the Paradiso method is an explicit solver. It runs faster, probably better for smaller models, whereas the other method, FGMRES models, are implicit. They're iterative solvers. They work by using successive approximations, and they're more efficient for larger 2D models that would otherwise take forever to solve using Paradiso, some explicit method. But the GMRES stands for Generalized Minimal Residual Method. Below that, we have an implicit sediment weighting factor. So 1 means it's completely implicit, and then 0 means it would be completely explicit. You'd really only set this if you were using an implicit method to sort of vary between implicit and explicit. If I set it to 1 and it's fully implicit, this is going to be more accurate but less stable. And then closer to 0 or 0 itself would be less accurate, more stable, and it controls the balance between the current and previous time steps when solving sediment transport equations. All right, below that we have outer loop convergence parameters, where we have control to specify the maximum number of iterations for sediment equations, as well as convergence criteria down here. Now, the outer loop refers to, let me take a step back and just say that sediment transport involves two sort of sets of equations. There's outer loop and inner loop. Inner loop refers to the sediment concentration, that's the focus, and then outer loop is focused on flow, sediment transport, and bed change. The two loops are used to decouple complexity, numerical stability, and improve computational efficiency. So regarding the outer loop here, the default value is 5. If, for instance, all of your calculations are bumping up against this maximum number of iterations, you may need to increase that maximum number of iterations, or you may need to increase the tolerance. You may be too tight with the tolerance values. The tolerance values you're seeing here refer to the concentration of maximum absolute error as well as root mean squared error. And then there's this third one here for grain size percent, maximum absolute error. So go ahead and play around with those tolerance values if necessary. Below that, we have the computation sediment layer parameters. This is optional, but what it does is it allows the user to subdivide the sediment depth, not only based on gradation, but by computation. We saw in the previous lesson, lesson 91, called Defining 2D Sediment Data, how to define that sediment bed, the riverbed, with different depths and different gradations. That's what I would call bed layers. But HEC RAS now introduces the concept of computational bed layers. So let me bring up the user's manual. Here on the left, we have the bed gradation. Say we have one gradation. That could be divided up into multiple computation bed layers. Or further down below, we have another example. Now we have 3 different layers in depth with different gradations. And then the computational bed layers are shown over here on the right. So the number of computational bed layers has to be at least the number of user-specified initial bed layers. So for instance, gradation here only has one computational bed layer, but gradation B and C have 2 and 3 computational bed layers respectively. Okay, back to HEC RAS and back to our interface here. Below that, we have subgrid data. This refers to the different subcell erosion methods, and as not only erosion, but also deposition. That's what these two drop downs are for. The constant method is the simplest method. Each cell is a single erosion potential, and it's computed based on hydraulics and bed properties. So in HEC RAS, the erosion is equal to the erosion potential times the bed availability of erosion. The user's manual also mentions a depth weighted method in this dropdown, and I'm just not seeing that. Same here, no depth weighted method, so sorry about that. But it does mention the full grid method. This is the most computationally expensive method, and it requires subgrid hydraulic properties such as the velocity, shear stress, and shear velocities. As is the case with erosion method, the deposition method, veneer is the quickest and simplest, and then capacity weighted method is the most computationally complex. And down below that, we have some optional ways to resize the region of the subgrid, either by region, setting the max subgrid regions or max subgrid length scale. All right, well, that is it for this lesson. What we talked about was the 2D sediment options and tolerances within HEC RAS.